This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Let's move on with the lecture. There is a lot of descriptive chemistry that we're going to be talking about today. And so it can look as though it's very overwhelming. Do you need to know every fact on every slide? Is everything required knowledge for the exam? What I'd encourage you to do is look for the themes. Okay, look for the patterns that we see in the chemistry. I will put particular emphasis on the points that I expect you to know for the exam. Okay, so if I emphasise a particular structure or a particular compound, make sure you know that. Okay. All right. So we've been talking about allotropes of carbon. We spoke about diamond and Lonsdale-Light, and we said that they were based upon tetrahedral carbon centres, sp3 hybridised. And one of the themes that I'd like to develop is that it's not so much the identity of the element, but rather the structure which gives it a compound or a material its physical and chemical properties. And this is really nicely illustrated with graphite here. In graphite we have these trigonal carbon centres there, and we can see we have angles of 120 degrees. That is a flat sheet, and we've got perpendicular to that sheet a p orbital, and for each carbon atom we've got one electron in that p orbital. And those p orbitals are overlapping above and below that sheet. Okay, so we have covalent interactions within the sheet, and then we've got dispersion forces between the sheets. Now each bond, each carbon-carbon connection may be considered to be 1 1/3 bonds, and that's because each carbon formally forms 4 bonds. We have 1, 2, 3 single, but with the overlap of the p orbitals we get an extra bond in there, and so the average bond length, or the average bond, is 1.33 bonds between a single and a double bond. Okay, so in the extended structure we have the sheets stacking on top of each other and while this bonding within a sheet is very strong, this intersheet interaction is much weaker. And so as a consequence these layers can slide past each other. So if you've ever felt graphite, it's got a very much a slippery feel. It's a very soft material with the layers being able to slide past each other. Contrast that with diamond, hardest substance known. Same element, but in this case we get the sheet structure. In diamond we have the three-dimensional network structure. So it's the structure rather than the element which is responsible for the properties. Intercalation can also occur with something like graphite. It's because it is only weak interaction between the sheets, we can put things in between the sheets. If I expose graphite to something like sodium vapour, the sodium can give up its electron, that ends up being delocalised on the sheet, and the sodium cation can then be located in between those particular sheets. Okay, so that's graphite. And closely related to graphite is this molecule here, or this class of molecules known as the fullerenes. And I can remember being a student, a research student in the 1980s, and a lecturer came back from the UK where he went to a conference. They said they've discovered a new form of carbon. And this was really big news at the time because everyone thought, well, carbon was diamond or it was graphite. What was this new form? Well, it was a soluble form of carbon, and the NMR spectrum showed a single carbon resonance. But they knew that the molecule from mass spec had 60 carbon atoms. And they thought, well, how can this actually be arranged so that we can have 60 carbon atoms and we've only got a single resonance? And what people proposed was that we had this spherical shaped molecule with the 60 carbon atoms, and that resembled a soccer ball. And if you look at a soccer ball, you can see pentagons and hexagons, and that's what we have here. Now, each of those centres is close to being trigonal planar, but not quite, slightly pyramidal. But given that fact that it is close to trigonal plane, that these are sp2 hybridised carbons. And again, we have the overlap of the p orbitals in that particular case. But it's all sp2 in that particular case. So after the discovery of C60, other carbon cages were discovered. So the C70 is quite a common form of carbon. These are known as actually buckyballs. And even molecules as big as this carbon 540 were discovered. And that work ended up winning Smalley, Curl and Croto the Nobel Prize in 1996. And people thought, this is wonderful, these are fantastic molecules, we'll use them for all sorts of things, but they never lived up to the hype at all, unfortunately. Great, they look fantastic, but what can they do? Well, some work that did emerge from that, which does give us some technologically useful materials, is the work relating to carbon nanotubes. So imagine we take the graphite and we roll it up like a newspaper. Take the sheet, roll it up into a tube. If we do that, we can get something like a nanotube here. So again, sp2 hybridised carbons, trigonal carbons here. And we have just hexagons in that cylindrical tube there. Now if we get near the end, we actually get some 5-membered rings. See that one there? And that enables the tube to curve around and close off at the end. We can have different types of carbon nanotubes. In this case here, we've got the carbon-carbon bonds there, and they're actually perpendicular to the direction of the tube, whereas in this one, they're parallel to the direction of the tube. In the last one here, we've actually got a twist in the tube, and that twist makes that tube chiral. Okay, so they're the carbon nanotubes, and technologically they are important. They have useful properties. The single-wall nanotubes, diameter of about 1 nanometre, excellent conductors of electricity along the direction of the tube, about 1,000 times better than copper. They have tensile strength, and they are directional thermal conductors, and they are very expensive. If you try to make them, generally you make these multi-walled nanotubes, which are like a tube inside a tube inside a tube, like a telescope. And they are not so useful. Okay, the technological properties of those are not that impressive. Okay, so we've looked at all of these carbon allotropes. The sp3 hybridised ones, the diamond and the Lonsdale-lite, and the sp2, graphite, and the buckyballs and the nanotubes in that particular case. The point I want to emphasise there, it's not the actual identity of the element, it's the structure which is important in determining the properties. Let's just go down the group there, the group 14 elements, as we go down through silicon, germanium, tin and lead, and we move from carbon, which is certainly a non-metal, to silicon. And silicon has a structure very similar to diamond. We can change the structure. There is another form of silicon which has a little bit more metallic character. We go down to germanium, that's similar to silicon. And we get down to tin, we consider tin to be a metal. Okay, and finally lead, that is certainly a metal. Tin does adopt a form which is slightly or less metallic at low temperature, but the general trend is to go from carbon to lead, we're going to a greater metallic character, crossover point somewhere between germanium and tin, we might say, we cross over to a metal. Let's look at the group 15 elements. We start off with nitrogen, and nitrogen is a very stable molecule, and we can understand that stability just by looking at its strong triple bond. And as a consequence, N2 is often at the bottom of the thermodynamic well as far as nitrogen compounds are concerned. So lots of nitrogen compounds will decompose to N2 because it is so stable. If I wanted to provide an inert atmosphere for a chemical reaction, I'd often use something like nitrogen. It's often also used as a cryogenic liquid because it has a very low boiling point. Okay, let's go down the group. Let's see what trends we have as we descend the group 15 elements. And there's a really stark difference between nitrogen, which is incredibly stable, and phosphorus. This is white phosphorus here. And it's a very unusual type of molecule in that we say it's tetrahedral, but we don't have a tetrahedral atom at the centre. The phosphorus atoms are actually at the vertices of that tetrahedron. And we've got lone pairs coming off each of those phosphorus atoms there. Okay, so if that was wanting to be, if we thought about this phosphorus atom from a VSEPR point of view, we've got 1, 2, 3 bonds and a lone pair. That should be a tetrahedral centre. But because of the geometric constraints of the molecule, that P angle here is actually 60 degrees, not 109.5. So as a consequence, this is a highly strained molecule. And the fact that it's highly strained means it's very reactive. Okay, if you have white phosphorus, it gets anywhere near air, it'll catch fire. It's a highly reactive form of phosphorus. So it contrasts with N2. You can actually get an analogue of N2 with P2, but only at very high temperatures. Okay, so we can consider white phosphorus to be the most reactive form of phosphorus. Okay, and that's a consequence of its structure. I'll say that again if you like. I'm putting special emphasis on this. White phosphorus is a very reactive form of phosphorus because its structure is so strained. Okay, did everyone get that? Good. Okay, another form of phosphorus we can have is red phosphorus. And it's got this chain type structure. You can see in that it's got that P4 type of unit. So if we had a link between that phosphorus atom and that one, we'd have that tetrahedral unit. But we break that connection and link these units up into a chain. We reduce the strain. If we reduce the strain, we make it less reactive. If we reduce the strain, we make it less reactive. So red phosphorus is a more stable form of phosphorus than white phosphorus. Everyone get that? If we go to something like black phosphorus, this is a far less reactive form of phosphorus. It's a two-dimensional sheet and it's a lot more stable. Doesn't tend to react. If we go down the group 15 elements, go to something like arsenic. Arsenic can exist like white phosphorus as AS4 units, but the general trend is, as we go down from nitrogen, phosphorus, arsenic, antimony and bismuth, that we move towards metallic character. But really, it's only when we really get to bismuth that we get to a true metal. So, as we go look at the groups towards the far right-hand side of the periodic table, that transition to metallic character occurs later in the group. Okay, so in this case, only bismuth would be considered to be the true metal there. Okay, let's move on to the next set of slides. And I'll just close that. Okay, let's talk about oxygen. We're going to go through the same sort of routine here. Oxygen has this particular Lewis structure. It's a diatomic gas. It's got the double bond there, and we've got two lone pairs on each of the oxygens. The only trouble is the Lewis structure is not a satisfactory description of the electronic structure for oxygen. And the reason for that is that we know that oxygen is paramagnetic. We can put it into a magnetic field and it's attracted into that magnetic field. And therefore, it must contain unpaired electrons. So, what's going on with something like oxygen? Well, let's just think about this material O2. 20% of the atmosphere in this room is O2, where the room is filled with combustible material. I'm made of combustible material. My clothes are made of combustible material. I've got a very strong oxidant, O2, and I've got combustible material. Why don't I catch fire? Imagine the talking point tonight around the dinner table. Lecturer caught fire. And your family might say, well, not surprising given that he is combustible and all that oxygen around. But why don't I combust? Why don't I undergo spontaneous combustion? Well, it's to do with the electronic structure of O2. The fact, if we look at the molecular orbital diagram, that we've got two unpaired electrons with parallel spin. And because of that arrangement, because of having those two parallel electrons, what we call a triplet state, it's hard to get oxygen to react. Thermodynamically, reaction is favoured, but kinetically, the rate of reaction is slow because there's a big activation energy that needs to be overcome for the oxygen to react. So, the MO description for ground state O2 says it's a triplet dioxygen. The triplet state for the oxygen is not very reactive. The singlet state is much more reactive. What's the singlet state? Well, that's an excited state where we have the two electrons in the pi 2p star orbital, but instead of being parallel, they're anti-parallel, one up and one down, and that is a lot more reactive. Okay, so what are the implications of having the triplet state for oxygen? Well, certainly we can get combustion occurring in that particular case. But when we have combustion, because it's such an exothermic process, that energy that's released drives that reaction to occur. Okay, that overcomes the activation energy barrier. So the reaction can become self-sustaining because of the heat released. Another form of oxygen we need to be aware of is ozone, V-shaped molecule. And I'm sure that would have been covered in Dr. Jamison's lectures. You can see it's got the V shape like that. There's a partial positive charge on the central oxygen there and a partial negative charge distributed on the two terminal oxygens there. This is also a strong oxidant. In fact, it's a stronger oxidant than dioxygen. Still in the zero oxidation state though. So this is a blue diamagnetic gas, very strong and distinctive odour. You might sometimes smell it during a lightning storm. Whenever there's an electrical discharge, you can generate O2, or sometimes with electrical equipment malfunctioning. The spark can often generate ozone. If we take ozone and we combine it with lead sulfide, then it can act as an oxidant. So let's just look at lead sulfide here. We've got lead in the +2 oxidation state. We've got sulphur in the -2 oxidation state. So we can oxidise that sulphide to sulphate. It's going from the -2 to the +6 oxidation state there. And one oxygen from each ozone is responsible for that oxidation. So we end up producing O2. Okay. Let's look at some of the uses of ozone. Because of its oxidising strength, it can be used as a bleach, an alternative to using hypochlorite, which is commonly used as a bleach. There was some talk about, in fact, a few years ago, ozone pools were quite common, and that's because it's very good at killing bacteria. It's also used to purify air in the London Underground as well. Down at the ground level, ozone is quite toxic and is considered a pollutant. But in the upper atmosphere, it's absolutely critical for life because of the UV light it absorbs. So UV light is very dangerous to both plant and animal organisms, but having a decent concentration of ozone in the upper atmosphere protects us from that. If you think about the Earth and the evolution of the Earth that occurred, before there was any life on Earth, there was no oxygen in the atmosphere. And so the surface of the Earth was just bathed in UV light. And that's why scientists have proposed that life must have originated in the ocean, which was protected from ultraviolet exposure. And then as photosynthesis occurred, oxygen went into the atmosphere, and then ozone protected the land from UV light. All right, let's talk about allotropes of sulphur now. And we've got this contrast between oxygen and sulphur. You can get S2 in the gas phase at very high temperatures, but generally we get sulphur forms like this. This is S8, and each sulphur is forming two bonds. We can also get this thing called ketida sulphur, where we just have sulphurs forming chains or branch chains. You can also get S3 being formed. What if we go down the rest of the group there? Well, again, we see that slow transition towards metal type character. Selenium, well, three structural forms, and again, they're based upon Se8 rings, a little bit like we saw with sulphur. There is a metallic form called hexagonal selenium, and that does have helical chains with weak interactions between the chains, and that's photoconductive. If we keep going down, we get to tellurium. So selenium and tellurium, we don't normally consider them to be metals. Tellurium's as a network of spirals with strong interchain interactions. If we go down to the last member of that group, polonium, this is the closest thing to a metal in that group. It's got this simple primitive cubic structure. So it doesn't really have that metal type structure that we normally see, face-centered cubic, cubic closed packed body-centered cubic. This is just a simple cubic arrangement there. Okay, if we leave that there and we go to our last group, we're going to consider the group 17 elements. They're all diatomic species. For fluorine and chlorine, they're gases under normal conditions. For bromine, a liquid, but a very volatile liquid, and iodine is a solid. And the fact that we have an increase in the boiling points and the melting points reflects the fact that we have increased dispersion forces between those molecules. Any hint of metallic character? Well, what you do see for something like iodine is that sort of metallic luster with iodine. And if you can see that high reflectivity from a surface, then you're starting to have some sort of metallic character. Now, it's only weakly conducting iodine, but if you put it under pressure, then its electrical conductance will rise dramatically. Okay. Let's talk about some general observations. Pi bonding. Pi bonding is important for the period 2 elements, for nitrogen, for oxygen. Okay? In those particular elements, pi bonding is very important. But for the period 3 elements, it's less important. So we're more likely to get a polymeric structure or chains or rings for the period 3 elements. Another trend we saw was a trend towards metallic structure going down the group. So more metallic behaviour the further down the group we went. If we're looking for the later groups, the transition to metallic behaviour, it becomes quite late in the group. And the final point there, the physical and chemical behaviour is very much related to the structure of the element, not so much the identity of the element. And that's really nicely demonstrated by diamond and graphite and white phosphorus versus black phosphorus, with red phosphorus being intermediate. Okay? In particular, make sure you understand why white phosphorus is so reactive, red phosphorus less reactive, and black phosphorus barely reactive at all. Okay, let's look into the final section here. We're into the final lap, and we're going to be talking about the main group chemistry. I want to concentrate on the sorts of compounds that oxygen, sulphur, nitrogen and phosphorus form. If we're talking about oxygen, it's dominated by the -2 oxidation state. So we do see elemental oxygen as O2 and ozone. We do see oxygen as peroxide, where it's in the -1 oxidation state. But most of the time, it exists as the -2. So we might have an iron oxide, -2 oxidation state, carbon dioxide, a gas, -2 oxidation state, water, -2 oxidation state. Let's just talk briefly about water. It's a ubiquitous material, as we all know, ubiquitous on Earth, that is. That means it's everywhere. But we take it for granted. It truly is a remarkable compound with exceptional chemical and physical properties. And it's all a consequence of the fact of the shape of the molecule. The fact that it's bent means it has all of these wonderful properties that we see for water. If you compare it to things like ammonia, hydrogen fluoride, hydrogen sulfide, which you might consider to be its neighbours, if you like, in the periodic table, it's very different. And we can attribute all of these wonderful properties to its shape. Much of that has to do with its ability to form hydrogen bonds. So the fact that we have the electronegative oxygen, the electropositive hydrogen, and we have a polar covalent bond, we have a strong hydrogen bond. Now, if a lone pair is involved in forming a hydrogen bond here, that polarises the oxygen and makes that more negative. If that becomes more negative, that polarises this covalent bond, and this hydrogen bond here becomes stronger. So by acting as a hydrogen bond donor, acting as a hydrogen bond acceptor, as it is here, its ability to act as a hydrogen bond donor is enhanced. Okay, so this is a common environment for a water molecule. Okay, so because it can act as a double hydrogen bond donor, double hydrogen bond acceptor, it often behaves as a tetrahedral connector. And we can see that in the structure of ice. So here's part of the structure of ice, and we can see we've got these relatively large cavities here. Because of that open type structure, its density is less than the density of liquid water. So liquid water's got a density of 1 gram per centimetre cubed. This is 0.92 grams per centimetre cubed. Now you might think about that, well, if it likes to form these tetrahedral building blocks, can it form a diamond type structure? And in fact, at low temperatures, you can get a diamond type form of ice. And again, the density is 0.92 grams per centimetre cubed. Okay, now that can be related to diamond or zinc blend, whereas the other form of ice, the more traditional form of ice we see, can be related to Lonsdaleite and wurtzite. Sometimes you get a molecule which has the right size and shape to be incorporated into water, and the water can start to form hydrogen bonds around it. And that happens with methane. You might remember that we spoke a bit when we were doing Henry's law, we said methane was quite soluble in water. Well, one of the reasons is that we can include methane into water and it can nicely form hydrogen bonds around the methane, not with the methane, but around the methane. And the methane can be a template for creating these spheres of hydrogen bonded waters. So this is methane hydrate, which is a form of ice in which we've got methane molecules trapped in these holes. And we can set that alight as the methane evaporates. It can undergo combustion, but because it's essentially ice, you can hold it in your hands. I don't think I'd be brave enough to try that, but it looks like a lot of fun. Okay. Environmentally, this is really important because near the Arctic, they estimate there are enormous amounts of methane hydrates on the bottom of the ocean. In fact, the amount of methane there dwarfs what we have as oil reserves in the world. And people have said, well, can we mine it? Can we extract the methane, use it as a fuel in that case there? Well, environmentally may not be such a good idea. What concerns many environmentalists is that if that methane hydrate was to melt, If temperatures increased, the methane hydrate melted, we would release all of this methane into the atmosphere. And methane is a far worse greenhouse gas than CO2. So it's something we need to be thinking about. Okay, move on to liquid water. When we melt the ice, we disrupt the hydrogen bonds, but we also allow them to come closer. And so it turns out in liquid water that there's an average of 4.4 neighbours within 2.84 angstroms of water molecules. So the water molecules come closer together and we end up with something which has a higher density than the solid water, the ice. Hydrogen bonds in water, they're being broken and formed very, very quickly. The lifetime of a hydrogen bond, about 9.5 picoseconds, 10 to the minus 12 of a second. Just to put that in perspective, for light, it will only travel 3 millimetres in the time it takes to form and break a hydrogen bond. So this is happening at a very, very rapid rate. So pure liquid water, a random 3D network with a local preference for tetrahedral geometry. Okay, so here are some properties that we commonly associate with water. Its solvent properties, the fact that it can dissolve things like salts. Its high specific heat is a consequence of hydrogen bonding, as is its high surface tension. The density of liquid water, meaning that ice floats on top of water, is very important to aquatic life. Again, that's a consequence of the hydrogen bonding making a less dense structure. The high intermolecular associations leads to high viscosity, and the relatively high melting and boiling points is again the consequence of hydrogen bonding, all because it's a V-shaped molecule. If it was linear, it would be non-polar, it wouldn't exhibit any of these properties. Okay, let's move on to another oxygen hydride, and this is peroxide. You need to know the structure of hydrogen peroxide. You've got a single bond between the two oxygens, and you've got two lone pairs on each of them. So normally when we think of oxygen, it's in the -2 oxidation state in the form of water. Elemental oxygen, 0 oxidation state. This is in between, -1 oxidation state. So in peroxide, it can actually take another electron, go down to that nice stable -2 oxidation state, in which case it's going to be acting as an oxidant, or in some cases it can act as a reductant and go up to the 0 oxidation state. Here it is acting as an oxidant and taking the sulfide and lead sulfide to lead sulfate. But it turns out the peroxide is unstable, thermodynamically unstable. Look at the delta H value for this, -196, and this is for 2 hydrogen peroxides undergoing a process known as disproportionation. So it's at the -1 oxidation state. Some of the oxygen goes up to the 0 oxidation state in the form of O2. Some of the oxygen goes down to the -2 oxidation state in the form of water. So hydrogen peroxide, which you can store in a bottle, there's no problem storing it, but after a period of time it will eventually decompose to water and oxygen. So although thermodynamically unstable, kinetically it's stable enough to store. If you have a catalyst there, then that disproportionation reaction can occur very, very rapidly, sometimes explosively. Let's move on to sulfur compounds now. And for sulfur we see a much wider range of oxidation states, and that's because sulfur is not as electronegative as oxygen. Oxygen we only see 0, -1, -2. Sulfur we see -2, 0 in the form of elemental sulfur of course, +2, +4, +6. When it's in the -2 oxidation state, there's clear similarities with oxygen. So zinc oxide, zinc sulfide, similar sort of materials. Water, H2S, both triatomic molecules. H2S, very, very nasty material. Highly toxic, more toxic than hydrogen cyanide. The good thing about it is, though, that it's such a foul-smelling gas that in tiny concentrations we are able to detect it. Okay? It's worth just thinking about the sorts of things that we can detect by our sense of smell. If you think about it, a lot of the smelly things have one thing in common: lone pairs. So you might like to think how those actual molecules might be interacting with things like proteins, which might contain metal atoms like zinc. Okay, so people have proposed that when molecules come into your nose, they're interacting with the metals in proteins, and that's being transformed into a signal to give to sense that particular molecule. That's irrelevant to anything we're talking about here. But H2S can lose a proton, it can go to HS minus, and then HS minus itself can lose another proton. So we can consider H2S to be a diprotic acid. It's only a weak one, but it can lose both of those protons. The hydrogen-sulfur bond is not very polar, and so hydrogen bonding is not important. That's why hydrogen sulfide is a gas. The intermolecular associations are extremely weak. What about oxides? Well, we can have sulfur monoxide. This is very rare, very unstable. We do have some pi bonding there, but that's much weaker than the bonding in O2. A much more stable form is sulfur dioxide. If we just take sulfur and we burn it, it burns with a blue flame, we'll generate SO2. This is the +4 oxidation state. Now that's an 18 electron molecule, just like ozone. And just like ozone, it's got a V shape. Okay, and that's used as a fruit preservative and antibacterial agent. If we want to go to SO3, this is the highest oxidation state we can go to for sulfur, then we need to combine it with oxygen and we need a catalyst. So it's really quite interesting. I burn the sulfur, I go to SO2. If I want to go to that next step, I need to have a catalyst present, something like a platinum or vanadium oxide. In the atmosphere, though, when you've got SO2 in the atmosphere, and that might be there from volcanic eruptions or from the burning of fossil fuels, once you get SO2 in the atmosphere, if there's particulate matter like dust or ice crystals, they can provide a catalytic surface for the conversion of SO2 to SO3. And once SO3 forms, we're in trouble, because SO3 can combine with water to give sulfuric acid, which can come down as acid rain. We might say a word about that a little bit later on. Okay, so this is SO3, and this is a planar molecule. This is one representation. Okay, so we've got a double bond between each of the oxygens. You can write a representation here with one double bond and two single bonds, and then put formal charges on the oxygens and the sulfur. But no matter which way you look at it, it's a flat molecule. SO3 is a flat molecule. We expect you to be able to work out that SO3 is a flat molecule. Okay, this is an important slide, because this is part of a theme that I'd like you to be aware of. If we take a main group element oxide and we combine it with water, we form an acid. So SO2 combined with water will form sulfurous acid. Now there's no change in oxidation state here. We have +4 sulfur oxide, we have +4 in the sulfurous acid there. So if you think about it, it's a little bit like carbonic acid. Now this is not an overly strong acid in the case of sulfurous acid. We can take salts of sulfurous acid, so we can remove the hydrogen atoms and we can end up with a metal salt. We can have sodium sulfite, or we can have sodium hydrogen sulfite, Again, there's parallels there with the carbonate. But look at the structure here. I want you to be aware of the structure of SO3 2- compared to the structure of SO3. We have an extra 2 electrons, so where do they go? They're a lone pair on the sulfur. So we have a lone pair of electrons on the sulfur atom in SO3 2-, and it's got that pyramidal shape. So be aware of that, those two shapes, SO3 and SO3 2-. Okay, if I take that SO3, if I oxidise that SO2 to SO3 and I combine that with water, I can generate H2SO4. Now there are other ways of generating H2SO4, but generally it involves taking sulphur in a +6 oxidation state and combining it with water. If I try to do that reaction, I'll form, because it's such an exothermic reaction, it forms a very fine mist. It's very hard to collect the product. But the production of sulphuric acid is higher than any other industrially produced chemical. And that's because it's used in so many different technologies and industries. So the manufacture of fertiliser, pigments, iron, steel, petroleum products, synthetic polymers, papers, etc., sulphuric acid is used. Why? Because it's a strong acid, it's a good dehydrating agent, and it's also a good oxidant. The sulphur's in the +6 oxidation state, that makes it a good oxidant. People have proposed that the sulphuric acid production levels provides an indication of the strength of the industry in a country. Okay. Let's just look at sulphuric acid in a little bit of detail here. Here we've got 3 forms of sulphuric acid, the diprotonated form, the hydrogen sulphate form, and then the sulphate form. Just be aware that as I remove hydrogens, as it's acting as an acid, I don't change oxidation state. I might change the charge on the species, but I'm not changing the oxidation state. It's +6 in all of those 3 species. The sulphur stays in the +6 oxidation state. Acting as an acid doesn't change oxidation state. We just mentioned acid rain before. So if this reaction occurs in the atmosphere, where we've got SO2, interacts with those fine particulate matter, the dust, etc., gets converted to H2SO4, which is, of course, a very strong acid. Now, the consequence of that is that when the rain falls, we have a very low pH. So the pH of natural waters is lowered, and that can affect all of the aquatic life in the waters. It can have a bad effect on forests. In fact, a lot of forests in northern Europe have been wiped out by acid rain because the pH has dropped. Buildings and statues, they are also susceptible to sulphuric acid because they're made of things like calcium carbonate, and on exposure to acid, that can break down to carbon dioxide. Okay, we've now got down to our last 2 elements. We're going to talk about nitrogen hydrides and oxides, and then phosphorus hydrides and phosphorus oxides, and then we're done. So most of us know the structure of ammonia, pyramidal structure, lone pair. Nitrogen is a wonderfully generous atom, very keen to share its pair of electrons, and if you go on in chemistry next semester, you'll see lots of examples of organic chemistry where nitrogen acts as a nucleophile, an electron donor, if you like. Hydrazines, perhaps we don't hear so much about that, but it's a very important compound that's formed just from the combination of nitrogen and hydrogen. It's a lot of hydrogen bonding occurs with hydrazine, and that's because we've got lone pairs on the nitrogen and we've got the NH covalent bonds. So this was one of my favourite exam questions for quite a few years. I used to ask students to draw me the structure of hydrazine, N2H4. And so what students would often do is draw nitrogen with a double bond and then 2 hydrogens coming off. If you do the electron count, however, there's too many electrons. So rather than have a double bond, we've got a lone pair on each of the nitrogens there. So it's really almost like two ammonia molecules. Get rid of a hydrogen from each and put a direct nitrogen-nitrogen bond. Hydrazine is pretty unstable with respect to nitrogen, and it can act as a reductant, a very powerful reductant. If combined with oxygen, we get this highly exothermic reaction, and that's used to propel rockets. Okay, so make sure you know the structure of hydrazine. Let's look at the nitrogen oxides, and there's a really rich chemistry associated with nitrogen. Every oxidation state between -3 and +5 is represented for nitrogen. We can have N2O, that's dinitrogen monoxide, or nitrous oxide, or more commonly known as laughing gas. Okay, so that's given to patients, particularly women in labour, might use the nitrous oxide. Also some anaesthetists, especially the older generation of anaesthetists, will use N2O in their inhalation anaesthetic mix. NO, the radical species, that's nitric oxide. That's commonly produced from the combustion of fuels in automobiles. Dinitrogen trioxide, we don't hear so much about that, it's not that common. NO2, this is a real problem. If it's a very still day in Melbourne, often you'll see this brown haze over the city, and that's due to NO2. NO2 has got an unpaired electron, that gives it its colour, and that's environmentally a very nasty material. That can dimerise to give us N2O4, and then finally we've got the dinitrogen pentoxide, the +5 oxidation state. We don't see nitrogen commonly in that form there. So the most important oxides are nitrous oxide, NO, nitric oxide, and NO2. Okay, this is one of these slides that I'd like to pay particular attention to, and I think you should pay particular attention to this slide as well. If I take nitrogen oxide and I combine it with water, I will get nitric acid. It's that same theme again. Main group element oxide plus water gives me an acid. But there's also some redox chemistry going on here, in that we're starting off with the nitrogen in the +4 oxidation state, and the nitrogen ends up in the +5 oxidation state in the form of nitric acid, and we also get reduction to the +2 oxidation state in the form of nitric oxide. Okay, but it's another example of a main group element oxide reacting with water gives an acid. The higher the oxidation state for a given element, the stronger the acid. Okay, our last element, phosphorus, the hydride, phosphine. You can see that's really the cousin of ammonia, but it is nowhere near as strong a base as ammonia, so it's less likely to form the phosphodium pH4+ cation. This is a really highly toxic molecule, really too dangerous to use in the laboratory. Diphosphine is analogous to hydrazine. Okay, let's look at the oxides that we see here. And this is an interesting reaction. Here's our highly strained P4 molecule. Now, if I combine that with oxygen, and I limit the amount of oxygen, what I can do is I can form P4O6, and you can see the driving force for that, because what I'm doing is I'm breaking these phosphorus-phosphorus bonds, and I'm relieving the strain in that particular molecule. Okay, so I've put the bent oxygen in between those two phosphorus atoms there, and I've generated this molecular shape, which some of you might recognise as familiar, as being like 4 cyclohexane type rings in chair conformation. But the OP-O angle here, 102 degrees, so it's like it's relief, the strain is broken by the oxidation in that particular case. What if we have excess oxygen present? Well, we end up with P4O10. We put an extra oxygen on each of those phosphorus atoms. There was a lone pair there, but we put an oxygen, double bond oxygen in there. Now, P4O10 is a very effective drying agent. If there's any water around, it'll absorb it from the atmosphere. What do you think will happen if I take P4O10 and react it with water? It'll give me an acid. Okay, so it's another example of an elemental oxide reacting with water to give an acid. You'll notice the similarity of this particular unit here with the structure of diamond. And this is a type of structure that we see time and time again in chemistry. Very common. Okay, so this is our last chemistry slide for the semester. If we take P4O6 and we react with water, we get phosphorus acid, also known as phosphinic acid, H3PO3. That's what it looks like. We've got two acidic protons, but this third proton here is not acidic, which means that phosphorus hydrogen bond stays intact. The oxygen-hydrogen bonds, of course, can be broken. It can lose H+. Now, this is a much weaker acid than phosphoric acid. And that's because that oxidation state here is +3. It's +3 here, it's +3 there. Here it's +5. There it's +5. And we get this particular triprotic acid, which can lose up to 3 protons there. Okay. So, finally, let me just say, when you get to the exam, pay particular emphasis to the things I emphasised in this lecture. Okay? I think I gave enough clues to that. Make sure you read your questions carefully. Don't be put off and say, I can't do that, that looks too hard. Chances are they're not as hard. The questions are not as hard as what you think they might be. So please read the question carefully and think about it. Don't panic. Finally, I'd just like to say it's a real pleasure lecturing the first year class. I've loved doing these set of lectures. Thanks for your attention, everyone, and the best of luck for the future. Thank you. I'm not sure exactly how it's done, but I'm imagining that they're capturing the air and then they're treating it with the ozone, removing the ozone, and then recycling the air. So it's not constant the ozone? No, you're not putting ozone into the actual gas itself. It's very good at, because it's quite powerful oxygen, you can smell the salt smells and stops the oxygen. Today, it's your last lecture? Yep. Turn off. It's so much to get through that.